Okay, so welcome everyone. Today we are very happy to have Luca Iliesiu from Stanford University, and today he's going to tell us about new forms of attractions indices from gravitational path integral.
Great, thank you very much for the invitation. It's a pleasure to be here. I'll be here till tomorrow evening if you want to talk some more. So today I'll be telling you about how to compute supersymmetric indices directly at the level of the gravitational path integral for black holes. And what we'll discover is a new form of what used to be called the attractor mechanism, adapted for solutions that compute an index in Euclidean signature. So this is work done in collaboration with Joaquin Toriaci, Murat Polovlu, and Samir Murthy. So one of the most celebrated achievements in string theory is that through a string theory microstate count, people have managed to reproduce the entropy of black holes. So this is a result that probably most of you have heard about by Strominger and Vafa, but let's unpack this result a little bit further and let's be a bit more precise. Well, what people actually computed on the left-hand side when we're talking about the string theory count is people computed a string theory index at weak string coupling. An index is a difference between bosonic and fermionic states in a theory. And what this was compared to was not actually the entropy of a black hole directly, rather it was the area of an extremal black hole in a sector of fixed charge. The reason why these black holes needed to be extremal at the time is because those were the supersymmetric solutions that were known at the time that were supposed to match the string theory count. However, there are three problems with this equality, at least three problems. Let me tell you what they are. So the problem number one is that the right-hand side is at most degeneracy in the limit in which the temperature of the black hole goes to zero. I say at most because here one can assume that the area of an extremal black hole gives its entropy. As we will see shortly, this is not actually always true. So even if one accepts that the right-hand side is the degeneracy of a black hole, that's not what the left-hand side is computing. The left-hand side, an index, is defined for any temperature and counts a difference between bosonic and fermionic states. So bosonic and fermionic states have opposite signs. So if we want to make this equality precise, we should be comparing apples to apples. Namely, on the right-hand side, we should also be computing an index. On the left-hand side, it's actually impossible to compute the degeneracy in general because that would require a calculation at a very strong coupling. So that's unlikely. So instead, we should try to compute the index of a black hole directly. And this has been a long-standing problem. In fact, in the early days of ADS-CFT, the long-held belief was that indices on the boundary side receive no contributions from black hole solutions. So this was in Whitman's original paper. But as we will see today, this belief is somewhat incorrect. And in fact, there are Euclidean black hole solutions that contribute to an index.
I'm confused. I thought what Strominger and Vafa were arguing was that basically there weren't any fermionic black holes of the type they were counting. And so
they didn't, well,
so that the index and the black hole entropy were the same.
That was an assumption.
Yes.
There is no argument in their paper that said that there are no fermionic black holes. So the point is to try to compute in a general setup the index directly and to compute it for any temperature, just like the left-hand side.
Right, but that's different than saying that indices receive no contributions from black hole solutions.
Well, this is what was stated in the early days of post-Strominger and Vafa. For instance, in the reason why people stated this is because circles for black holes, usually the time circle is a contractible circle in the geometry. While as we shall see shortly, the index computes a trace with a -1 to the f insertion. And people believed that because of this -1 to the f insertion, there could be no spin structure that could be associated to the black hole geometry that would allow the fermion to actually be periodic around the thermal time circle. So that thing is actually not true. And I'll explain in a second why. It's a confusion about which circle is contractible that caused this confusion 20 years ago.
Okay.
The second problem is that even one should question, as I kind of alluded to before, whether the right-hand side, namely the area of the black hole, really captures the degeneracy of quantum system at extremality. And an important lesson that we've learned in the past couple of years is that classical extremal solutions are actually not trustworthy when one includes quantum corrections. Now, let me be more precise why that's not the case. Namely, in a paper of Sen and collaborators from more than a decade ago, they found that when one considers an extremal black hole solution that has a near horizon geometry that looks like ADS2 times S2, this is a portrayal of how ADS2 looks like. There are actually perturbations of the metric that do not change the Einstein-Hilbert action or Einstein-Maxwell action associated to the solution. So these are called the zero modes, and there's an infinite set of zero modes for this metric. And in principle, to actually compute the partition function of these black holes reliably, one would have to integrate over all possible such zero modes. The question is, how can one make sense of such an infinite dimensional integral? The answer, the modification to the partition function depends on this regularization of these zero modes. In principle, the volume of these zero modes that's regularized could be zero, could be infinite, could be a constant, we don't know. So what people have identified is that if one goes slightly away from the extremal limit, so if one modifies the metric by turning on a small temperature, so this is just changing the classical background on which one does the computation, and one considers exactly the same modes of the metric that used to be zero modes at extremality, these modes are no longer zero modes. Namely, when in the quadratic expansion of the Einstein-Maxwell action, they have a weight at quadratic order, and their weight is given precisely by the temperature. So now we can do the calculation and integrate out these modes exactly to obtain what the temperature dependence of the partition function is. So for instance, for an Einstein black hole in an Einstein-Maxwell theory in a sector of fixed charge, so we fix the temperature and we fix the charge of the black hole and do the quadratic expansion, what one finds is the following result. At leading order, there is an entropy term coming from extremality. This S0 is just pi q squared. It's just the entropy of an extremal black hole. Then there's a deviation coming from the extremal entropy that's linear in T. And then all these other results are perturbative corrections. And there are two types of perturbative corrections. The perturbative corrections that come from modes that were not zero modes in the calculation. And these give a correction that's logarithmic in the area of the black hole. And the perturbative correction coming from the modes that used to be zero modes at extremality. And importantly, these give a power law correction in the temperature. Now, why is that important? Well, that's important because notice as the temperature goes to zero, this one loop determinant factor can actually dominate in the partition function of the ensemble. And that's because at low temperature, what's happening is that these modes have a very, very light mass. So they actually become very strongly coupled. Their quantum fluctuations can be very large. So to see how big of an effect this one loop term has, let's look at the density of states coming from this result. So we can take the partition function that I just showed you, this partition function, Laplace transform it to get the density of states. And here at very large energy, the center of this plot is the energy that an extremal black hole would have. At very large energies above extremality, you see two plots. The curved plot is the one in which you neglect the effect of the, the dashed plot is the one in which you neglect the effect of these zero modes. And the solid plot is the one in which you keep these zero modes into account. So at large energies, you see that the two plots almost coincide. The density of states predicted semi-classically is pretty much correct. But as you approach extremality, you see that below this energy scale, the two plots start deviating a lot up to the point where exactly at extremality, the density of states goes to 0. So in other words, if I compute the entropy of a black hole at very, very low energies above extremality, then the entropy of these black holes is not given by their area. This plot has entropy given by area, this plot does not. So what about the supersymmetric cases? Is it really true then that in the supersymmetric cases, the area of the black hole computes the entropy?
So can you tell us a little bit more about the zero modes? What do they physically do to the solution?
Yes. They're basically a set of large diffeomorphisms of the metric that act non-trivially at on the boundary that glues the ADS2 times S2 portion of the spacetime to asymptotic flat space. So it changes the way in which ADS2 times S2 is embedded in the entire geometry. You could write what these perturbations of the metric are very explicitly and just check that they have 0 weight in the quadratic expansion. So for supersymmetric black holes, there is a difference, which is that we have to work in a theory of supergravity. And there are more zero modes. Just like before we had zero modes of the metric, which came from large diffeomorphisms, in supergravity, we have zero modes of the gravitino that come from super diffeomorphisms. So roughly speaking, the path integral over these zero modes at zero temperature now changes when I turn on a small temperature.
Is there no charge fixed at infinity?
Sorry?
Is there no charge that you fix at asymptotic infinity?
Yeah, you fix that charge, you fix Q.
No, but that's just true. But now you have an infinite algebra of infinities. BMS like. Wouldn't you fix an angle value charge at infinity to fix the zero mode? Each of them is changing some.
So at infinity, you fix you put the Dirichlet boundary conditions on the metric. You mean at infinity and R3 times S1. At like really asymptotically flat infinity.
Yeah.
So there you fix the Dirichlet boundary conditions to impose that the space is like flat space and that the time circle is periodic. And these large diffeomorphisms that exist in these ADS2 region turn out to like decay if you go to the flat space region.
So decay in a way that there's no concern.
There's no, yeah.
I see.
A naive question about this plot. Isn't it supposed to be convex? Or is there not an issue that the specific heat is positive everywhere here? This is basically e to the s.
Yes.
And
Yeah, I believe it.
it satisfies what it needs to satisfy.
Yeah, I believe so. Yes. Well, in fact, we know physical systems that have a density of states that looks exactly like this, that have a unitary Hamiltonian. One example is SYK. Like if you simulate SYK on a computer and plot its density of states obtained by just diagonalizing the Hamiltonian for a single member of the ensemble, you plot the histogram of its energy levels. It looks exactly like this. This has no assumption about the connection between these black holes and SYK. It's just that in some sense, they're both in the same universality class. Okay, So let's now see what happens. I won't explain the calculation beyond just what I said for supergravity, for black holes and supergravity. But if I do the same calculation and take care of the zero modes that existed at extremality for the metric and gravitino, you now find this modified density of states, where again we see that at high energy, the semi-classical result agrees with the result in which one includes the quantum corrections. But as you lower the energy towards extremality, what one finds is that the density of states exactly vanishes in an interval about extremality, and instead one finds an exact degeneracy at extremality whose value is given by e to the s naught times some one loop determinant factor. So since S naught was the area of was given by the area of the extremal black hole, here you find that the entropy is approximately equal to the area, but only because you are studying supersymmetric black holes that had a different set of quantum fluctuations that conspired exactly in such a way for the density of states to give you a support at extremality. And a final reason why you can't view these why the classical solutions kind of go bad in the case of both non-supersymmetric and supersymmetric black hole is because one can compute various probes of how the geometry looks like once you include quantum corrections. So for instance, in this recent paper by Maldacena and collaborators, they computed what the length of the Froth is for a two-sided extremal supersymmetric black hole. And in classically, because extremal black holes have this ADS2 times S2 geometry, they have an infinitely long Froth. And therefore, the length of the Einstein-Rosen bridge for a two-sided extremal black hole would be twice the length of the Froth. And it would be infinite. So classically, this length is infinite, but when one includes quantum corrections, what one actually finds is that this length is actually finite and is given by the logarithm of the charge of the black hole. So that's a very surprising result that tells us that extremal black holes, whether supersymmetric or non-supersymmetric, are very subtle. And one should be very careful when computing their entropy, action, free energy, and so on. Which brings me to problem number 3, which is that many times you could say, okay, well, now you understood the problem of what the degeneracy of extremal black holes is in supersymmetric cases. But this brings up the problem that in several cases, the supersymmetric index computed in string theory doesn't only receive contributions from the extremal black hole, it also receives contributions from other extremal solutions. So how about what do we do with these other extremal solutions? These include multi-central solutions that capture the fragmentation of this ADS2 Froth. So these are called Majumdar-Papapetrou solutions. So you could take an extremal solution of charge Q and actually divide its charge into a larger set of charges, Q1, Q2, and Q3, that sum up to Q. And there's a static black hole solution in which there's an infinite Froth associated to each one of these charges, in which all these black holes are in equilibrium. The reason why these black holes can be in equilibrium, roughly speaking, is because the gravitational force, when n is equal to q, precisely cancels the electromagnetic interaction between the black holes. The second solution that we should take into account is the attractor solution, in which not only do we have this ADS2 times S2 Froth, but we also have scalar fields that can vary along the geometry. So one can ask what the effect of these scalars is. And then there are further generalizations of these solutions that like multi-center solutions that involve scalar fields that vary along the geometry as well. So how does one take all of these into account? The issue with several of these geometries, at least with the multi-center geometries, is that following the same strategy that we did for the extremal black hole is very difficult because we don't know what the static finite temperature solutions are that correspond to these geometries. Once you turn on the temperature, these black holes tend to become unstable and collapse into each other. Precisely because you slightly increase their mass without changing their charges. So the gravitational forces no longer cancel the electromagnetic forces. So in what follows, we will actually see an exception, and we will actually construct finite temperature solutions that are multi-centered. So our goal for today, as I've said at the beginning, is to resolve these three problems by directly computing supersymmetric indices using the gravitational path integral. So let me start with what an index looks like in any quantum mechanical theory. An index is, let's say we're interested in an index in a sector of fixed charge, where this charge is not an R symmetry of your quantum system. An index in a sector of fixed charge can be defined as the insertion of -1 to the f times e to the minus beta times some Hamiltonian. And if supersymmetry is preserved, then what one expects for such an index is that it captures the difference between the bosonic and fermionic degeneracies for BPS states. Namely, the energy EBPS is only fixed as a function of the charges Qi of this quantum system. And namely, the important thing that I want you to keep in mind, and this will serve as a check throughout this talk, is that indices have trivial beta dependence. Namely, if I just compute the log of the index, the log of an index is always just linear in the inverse temperature. And the coefficient of that linear term is just given by the BPS energy of such state. So how does one compute this in gravity? Well, let's try to think about what -1 to the f actually is. -1 to the f can always be written as e to the 2 pi I times the angular momentum generator that I'll call j along some direction if j is a generator of SU2. This suggests that if I insert e to the 2 pi ij in the trace, according to ADS-CFT, whenever I turn on a j in a partition function, it's as if I turn on a chemical potential for this associated charge. The chemical potential associated to an angular momentum is just an angular velocity. So inserting e to the 2 pi ij in the partition function tells us that in the bulk geometry, we should turn on an angular velocity in such a way that omega times beta, this is the Euclidean angular velocity, is equal to 2 pi times 1 plus 2 times an integer. This is just such that when, if j is integer, is half integer quantized, this shifts by n being an integer should not matter. Okay. So let's take this prescription of turning on an angular velocity and see what happens for the simplest black hole that we know. We'll take the simplest black hole and compute the Euclidean action at fixed temperature and all these values of omega. The simplest black hole that we know for which we can compute an index is just a charged black hole, and the solution that has non-zero angular velocity for a charged black hole is called the Kerr-Newman solution. Now, I won't bore you by showing you the metric of the solution. It's, as you guys all know, when you did your course in GR, Kerr-Newman black holes have a complicated form. I'll just show you what happens when you evaluate their on-shell action for fixed angular velocity. Here, I just showed, to give you some intuition, I just showed what happens when you evaluate the on-shell action for a Kerr-Newman black hole close to extremality. So in the limit beta going to infinity, and I just kept the first non-trivial term. So the leading term gives you the extremal energy, the extremal entropy, and this is the leading correction. Good. Now, the first option is turning on beta omega such that beta omega is equal to plus or minus 2 pi. Actually, the sign here does not matter. It turns out that there's a coordinate change that allows us to take beta omega from being 2 pi to beta omega being minus 2 pi. So these two solutions are actually the same at the path integral level. But something really remarkable happens, which is that if you evaluate, you take your GR book and you evaluate the Kerr-Newman on-shell action for this specific angular velocity, what you find is that its on-shell action takes the very simple form in which the action is exactly linear in beta. So this has exactly the form of an index that we alluded to earlier. It's a free energy that's linear in beta and correctly captures the extremal BPS energy and the extremal entropy. And moreover, the geometry that you get is that the finite temperature Euclidean geometry, in fact, has killing spinors. You can solve the killing spinor equation in this geometry, which means that people usually said that there are no non-extremal solutions that are supersymmetric. Well, this is an example of that in Euclidean signature. It's a solution that's supersymmetric in the sense that it has killing spinors, but it exists for any temperature. Now, option number 2 is that you could take beta omega to be 2 pi times 1 plus 2n, when n is different than 0 or minus 1. 0 and minus 1 gave you the values plus or minus 2 pi. And the action that you get, you can kind of see directly from this expression that the action that you get does not take the form of an index. If you plug in beta omega is 2 pi 1 plus 2n in here, you'll get terms that go like 1 over beta and higher powers of beta. And the geometry has no killing spinors. So what's happening? The gravitational path integral tells us to sum over all these saddles because all these saddles are consistent with the boundary conditions that compute an index. Well, what happens is that these solutions actually have a set of fermionic zero modes of the gravitino, if I work in supergravity, but have no killing spinors. So there are no superisometries that my integral over gravitino should be quotient by. So what happens in these solutions is that there are perturbations of the gravitino that again have no weight under the action. There's nothing that really can regulate them. And an integral over a fermionic zero mode that doesn't have a bosonic superpartner gives you 0. To give you a better intuition, these perturbations of the gravitino that are zero modes come from large super diffeomorphisms that are generated by the superpartner of this killing vector, which is partial tau. And in the case of the solutions that have n equals 0 or minus 1, what happens is that the superisometries, that's quotient by superisometries, precisely cancel this integral over zero modes in such a way that there's no longer an actual fermionic zero mode and you get a non-zero result. So all this is to say that only these two solutions with n equals 0 or minus 1 contribute to the supersymmetric index in a theory of supergravity. And the action that you get has exactly the form of an index, meaning that it has trivial temperature dependence.
So this is computed by quadratic fluctuations around the classical solution in the supergravity theory?
For the zero modes?
Well, just for both cases. I mean, just in general, you're starting with your classical background.
No, so here this is just the classical statement. This is just the action.
There's no determinants involved. There's no one loop.
There's no one loop determinants that I've evaluated here. The only one loop effect that I wanted to explain is the fact that these solutions that have n different than 0 and minus 1 have a mode that has no weight in the action to all orders in perturbation theory.
You have an extra fermionic zero mode.
And you have an extra fermionic zero mode, and that kills these solutions. Roughly speaking, because I'm studying a quantity that's protected by supersymmetry on the boundary, only this is an explanation of why only bulk geometries that have killing spinors contribute to that boundary quantity. And namely because if you don't have a killing spinor, there will exist a mode of the gravitino that will generate a supercharge on the boundary with respect to which your observable is invariant, and that will be a zero mode. Okay, so the take-home message so far, there are 3 take-home messages that I wanted to remember. Message number 1 is that there are geometries at finite beta that are supersymmetric, and those are the ones that contribute to the index. And these geometries are nothing exotic. They're just, you're literally take any solution that you have in your GR textbook, turn beta omega equal to 2 pi or 2 pi I, depending on your convention, and you'll find a supersymmetric solution. Message number 2 is that the free energy of the black hole index, the free energy, I mean the on-shell action, has only trivial beta dependence, even though the area of these black holes, we'll see later, has complicated beta dependence. So it naively seems that these black holes don't compute an index, but if you compute their overall free energy, they do. And message number 3 addresses this confusion that came about in the early days of ADS-CFT, in which there was this claim that there are no black hole contributions to an index. How come this is a black hole solution that contributes to an index? And the answer is that in these solutions that are rotating, in any curve solutions in Euclidean signature, the time circle is actually not a contractible circle. And the basic confusion that came about in the early days of ADS-CFT assumed that the time circle for all black holes was contractible. And if you actually look at the contractible circle, what happens to any fermionic field in your theory is that psi of tau and phi is anti-periodic with respect to rotations around the contractible circle, but it's periodic with respect to rotations around the time circle. So this is exactly why this path integral computes an index, because if you look at fermionic fields, these are the boundary conditions in both. Any questions so far? Okay. So how about the previously mentioned more general solutions? So far, we've only talked about the specific supersymmetric solutions. So what about multi-center black holes? So first, let's talk about multi-center black holes just in a theory of pure supergravity that has no scalar moduli. So one can actually write down the most general solution that admits killing spinors in 4 dimensions. This was done by Todd, who I think I forgot to mention in the 80s. And one finds that the solution has to take this following form, where U and U tilde are a set of functions that have to satisfy these equations. Because they satisfy these equations, they need to be harmonic functions that can have poles at locations xi and xi tilde. So I'll call the poles of U north poles and the poles of U tilde south poles. North poles I'll represent with red, south poles I'll represent with gray. In order for this space-time to be asymptotically flat, to look like R3 times S1 in Euclidean signature, or to look like Minkowski space, one needs the number of poles in U to be equal to the number of poles in U tilde. And one can solve from the equations of motion, one can solve for what the angular velocity of these solutions is. And one finds the following solutions. And similarly, one can solve for the electric and magnetic fields in these solutions. The important thing to notice is that if U and U tilde are different than each other, then the solution has a non-trivial angular velocity. That's number 1. And if they're different than each other, then even if asymptotically you might have a solution that only has electric charges, everywhere on the geometry, there's both an electric and a magnetic field. And that's because of the rotation, right? If you rotate the electric charges, you'll generate a magnetic field as well. So far, this is the most general solution that solves the local equations of motion, but we have to impose the fact that the space-time actually needs to be smooth everywhere. So we want to impose that there are no singularities in this geometry.
Magnetic charge is a dipole charge?
Yeah, here the magnetic charge is like a dipole charge,
Yeah, okay. Exactly.
That is centered at the North and South Pole. That is exactly why I called them the North and South Pole. If I want there to be no singularities, I want to make sure that the integral of omega around any infinitesimal circle in my geometry is vanishing, or can be made to vanish by gauge transformation or a coordinate change. So one can do the following trick. One can compute the integral of omega from this equation by using Stokes' theorem. The integral of omega using Stokes' theorem and the fact that u and u tilde is harmonic, one finds that the integral of omega on a cylinder that surrounds the north or south pole is given by the following values: 4 pi a times u tilde and minus 4 pi a times u, where a's were the residues at the poles of u and u tilde. So naively, because the integral of omega along an infinitesimal circle has a finite value, it seems that we have a singularity in this geometry. But we want to ask whether this singularity is a coordinate singularity or a real singularity in the geometry. And the way to check that, to check whether it's a coordinate singularity, is that you have to find the coordinate transformation that gets rid of this expression, makes integral of omega be 0. So one can consider the following coordinate change, where time gets shifted by some function lambda of xi, under which omega transforms like a gauge field, and one to eliminate these values for the integral of omega at these 2 points, one can choose this specific reparametrization of time that depends on the angle phi. That's the angle that goes around the axis that connects the north and south pole. Okay, the thing that we need to make sure is that this coordinate change is a valid coordinate change. So let's first look at this coordinate change in Lorentzian signature. In Lorentzian signature, time is not periodic, and therefore this coordinate change is only allowed if u and u tilde are both equal to 0. Because I want to change a coordinate change that's not, it's a local diffeomorphism, not a large diffeomorphism. So if it's either equal to 0, or it turns out that the other solution is for all the poles of u to completely agree with the poles of u tilde, meaning that the north and south poles are not separable, and I can't apply the Stokes theorem in the way that I just did. So if you look at that solution that has all the xi equal x tilde I, that solution has omega equals 0 because u would be equal to u tilde. And what one recovers is precisely the multi-center solutions that people discussed in the past, namely the Majumdar-Papa-Petri solution, for which the factor in front of dt squared has a double poles at x equals xi. So this recovers the old Lorentzian multi-center solution. But now in Euclidean signature, time, I want to compute the partition function, so one needs to make time periodic. And in this case, this coordinate change is valid if at the same time, while through change of t, T changes by a factor of beta. So this is only possible if A times U tilde is beta over 4 pi, and U times A tilde is beta over 4 pi. And one can actually solve in these solutions what the angular velocity of the horizons of these black holes is as a function of A and U tilde, or U and A tilde. And what one finds is this quantity U tilde times A is precisely 1 over 2 times the angular velocity of the black hole. So what the condition, the smoothness condition that one recovers is precisely that once again, we have beta times omega equals 2 pi. In other words, if I start with a condition, here I started the other way around. If you start with the condition that your geometry has killing spinors and write down the most general solution, you'll derive in Euclidean signature the condition that actually is needed to compute an index on the boundary side. Here there's a plus minus solution that comes from the fact that I can shift T in either T plus beta or T to T minus beta.
The temperature, does it have to be the same for each horizon?
Yes, yes. Well, temperature is the period of the circle, of the time circle that you impose at infinity. So that's the way in which temperature is fixed. It's through the boundary condition at infinity. And that means that all these black holes are in thermal equilibrium once you fix that. Okay. And one can solve the smoothness constraint that I wrote down in a little bit more detail. And one finds the following, that the smoothness constraint implies that if U and U tilde have a single center, for example, a single north and south pole, one finds that the residue of the pole of U has to be equal to the residue of the pole of U tilde and has to be given by the charge of the black hole. And one can also compute the ADM mass of these solutions. The ADM mass of these solutions has the property that it's equal to Q. And one can also see from these smoothness equations, so namely from this equation and this equation, one can also see that the distance between the pole of U and the pole of U tilde is fixed to this value that depends on Q and beta. And it turns out that the solution that I just described that has just one pole in U and one pole in U tilde is exactly the same as the finite beta Kerr-Newman solution that has killing spinors that I've discussed earlier. The only difference is that this solution is now generalizable for any number of poles in U and U tilde. So it's generalizable to the multi-center case. And so when omega beta is 2 pi, this geometry in which the horizon is along the line connecting the north and south pole has a diffeomorphism that takes it to the rotating Kerr-Newman solution. And the free energy of one can compute the free energy of this solution either by computing the on-cell action or perhaps more informatively by computing the area of this horizon that's along this line plus beta omega j. And the important thing that I want to emphasize is that I pointed to earlier, but it's much easier to see in this solution, is that the area of these black holes depends non-trivially on beta because it can, with a bit of algebra, you can see that it's equal to beta times the distance between the poles, the North Pole and South Pole. And this distance in a previous slide, we saw that it had some complicated dependence of Q and beta. So the area of the black hole has a complicated dependence on Q and beta. But remember that in order to compute the free energy, I also have to add this term that's given by beta omega j, where beta omega is equal to 2 pi. But j has a semi-classical expectation value, which is given by this value. And if I sum up these two terms together, you get something that is completely independent of, has this trivial temperature dependent that gives you the extremal entropy and the term associated to the BPS energy. We can think of this as an analog of the attractor mechanism. So the attractor mechanism was a mechanism in the 90s, which explained why the area of black holes was independent of the boundary conditions that you put on fields at asymptotic infinity. Here, what we're seeing is that the free energy of the black hole that computes an index is independent of the boundary condition or has trivial dependence on the boundary conditions for the size of the S1 that you impose at the asymptotic in the asymptotic part of the spacetime. And one can compute this extremal. One can compute the on-shell action for these solutions more generally for any number of north and south poles. So this is the generalization of the multi-center solution. And one obtains an on-shell action that again is completely consistent with the result for an index that has this as the BPS energy and this as the logarithm of the difference between the bosonic and fermionic degeneracy. And once again, each individual area for any one of these black holes has very non-trivial dependence on theta, but overall you see that the Euclidean action, the Euclidean on-shell action, takes exactly the expected form of an index. Okay, so the conclusion is that if you take a multi-center solution, the old multi-center solution that was described in terms of harmonic functions that had double poles at some locations that were the centers of the black holes, now can be extended to finite temperature to compute an index by just splitting these double poles into pairs of single poles. Having a north and south pole, where you could think of there being, even if, as Emil said, even if there are only electric charges at the centers, once you split them up and add angular velocity, what happens is that now you could think about each pole having an associated magnetic dipole charge. So in principle, the thing to still complete is to compute the volume for these moduli space of these solutions once all the smoothness constraints are satisfied. So these black holes can be any distance apart, and they might have a very complicated moduli space. So now let's go to even more complicated theories. So what about black holes and theories that have vector multiplets and supergravity theories that have vector multiplets in which you turn on scalar moduli at asymptotic infinity? So these are the old attractor solutions of Ferrara, College, and Strominger, and the multi-center solutions of Denef and company. And it turns out, let's first look at them in Lorentzian signature. It turns out that the metric has a very similar form to the metrics that we were studying earlier. Namely, they take this form where this function called the entropy function sigma of h is specified in terms of a vector of harmonic functions h, and has this complicated dependence that depends exactly on the prepotential of the theory that we're studying. But the idea is fairly similar to the previous solutions. Instead of having a single harmonic function, now you have a harmonic function for each electric and magnetic component for each one of your vector multiplets in your theory. The poles, the residues of H at each pole determine a vector which gives the charges of the black holes that you're interested in. So for instance, if I study a compactification on T6, I have on a diagonal T6, I have 4 sets of charges that I can turn on at each one of these centers. And the overall constant c that appears in this harmonic function h is fixed by the values of the scalar moduli that you fix at asymptotic infinity. And in the previous solution, the analog of the angular velocity for these solutions satisfies a constraint that's very similar to what we saw before, where we expressed omega in terms of u and u tilde. Here is given by a symplectic inner product between EH and H. And the important thing to notice is that, for instance, if the inner product of all my charges, if all my charges gamma are parallel, which makes their inner product vanish, then I have solutions that have zero angular velocity. But if they're not parallel, then an angular velocity needs to be turned on. And just like before, there's an analog of smoothness that you can obtain precisely like we did before by applying d to this equation and then using Stokes' theorem to write down what an integral of omega on any infinitesimal circle is. And in Lorentzian signature, the smoothness solution that Neff and company wrote down in the 2000s was that the intersection product between the charge of the black hole and the harmonic function evaluated at each pole is equal to 0. And this should be viewed as completely analogously to the smoothness condition that we got for the Israel-Wilson metric, which told us that the residue associated to the function u times the function u tilde evaluated at the pole needed to also be 0. The difference is that this solution has more non-trivial solutions, while this solution had only trivial solutions that gave us back the Majumdar-Papa-Petru solution. So if you actually solve for what this constraint gives you, it once again tells you that the entropy function, which gives you the emblackening factor, and these geometries have double poles at each one of these xi's. So they're more akin to the Majumdar-Papa-Petru in the sense that they have infinitely long throats close to any one of these poles. And at each double pole of sigma, there's a set of equations called the attractor equations, which turn out to fix the scalar moduli to values that are independent of the asymptotic moduli. So for instance, if I study the case with one vector multiplet, I have two possible scalars in my theory. The ratio between them is a gauge invariant quantity, and exactly at the double pole of this function, it turns out that this tau only depends on the asymptotic charges, sigma, and is independent of these constant C tilde that came by fixing the moduli to different values. And the area of the black hole is actually given by sigma evaluated at the residues of this harmonic function h. So it only depends on the charges of the black hole, it's independent of that constant c. And this supposedly gave you the entropy of the extremal black hole. Okay, so what changes in Euclidean signature? Let's repeat the analysis that we did for the Israel-Wilson metric for this more complicated solutions of supergravity. Well, just like in the Israel-Wilson case, the smoothness condition changes. So the intersection product between gamma and h is no longer 0, but is instead beta dependent. Here, sigma of x going to infinity is the asymptotic value of this entropy function as you go far away from the black hole. And these conditions are completely analogous to the conditions in which the conditions that we found in Israel-Wilson. And moreover, one can solve for the angular velocity of these black holes along each one of these axes that connects the north and south pole. And just like in Israel-Wilson, one finds that this intersection product gives the angular velocity. Each intersection product gives the angular velocity in such a way that the overall smoothness condition still tells you that beta times alpha is equal to 2 pi. So what we're computing once again in this most general solution that has Killing spinners is an index once we impose that time is periodic at the asymptotic boundary. And moreover, if one imposes these smoothness conditions, one finds that what used to be called the entropy function, now it's just the emblackening factor of the metric, has single poles instead of having double poles. So double poles meant that there were infinitely long throats in the geometry, which gave rise to these ADS 2 times S2 near horizon regions. Single poles means that the geometries cap out smoothly like a cigar. And the way to find these more general solutions that for which sigma has single poles is just like before. We can split the poles of the harmonic function h that were located at a single center before into pairs of north and south poles, where the unknown here are the new dipole charges associated to each north and south pole. The smoothness condition that I told you earlier fixes the distance between north and south in terms of beta, the moduli, and the charges, but does not fix the dipole charges. So in order to fix the dipole charges, one has to actually look at the new set of attractor equations on these geometries. And the attractor equations, I won't show them explicitly because they're an ugly set of algebraic equations, but what they don't turn out to fix the value of the moduli on the horizon of the black hole. So in this plot, I plot this ratio, this gauge invariant ratio of the scalar in one multiplet divided by the scalar in the other, along the horizon of the black hole. So in blue, you could see the imaginary part of, as an example, the imaginary part of tau. And you can see that it varies along the horizon of the black hole in contrast to the old attractor solutions in which the scalars were just constant at the horizon and got attracted to a value that they just depended on the charge. Here, the exact shape of this plot actually depends on the moduli that you fix at asymptotic infinity. But what you'll notice is that at the north and south poles of the black hole, the north and south pole are the ends of this plot, the blue plot intersects this red value. And this red value is precisely the attractor value that one found in Lorentzian signature. So what happens is that even though the black hole, the scalars vary along the black hole horizon, they still get attracted to the Lorentzian attractor value at the north and south pole of the black hole. And this in turn turns out to fix the dipole charges that are associated to north and south. So for instance, in this example that I gave earlier, the unknown dipole charges are fixed in terms of so this would be like the D6 dipole, and this would be the D2 dipole charges, and they get fixed in terms of the D0 and D4 overall charges of the system. And with that, the solution is now completely fixed. Just like before, it has an area and an angular momentum. The area and angular momentum, once again, both have complicated dependence on the moduli values. They depend both in B and on the values of the scalar fields at infinity that are captured through that function C that appeared in the harmonic function H. However, once you sum the area with beta omega j, and you impose the smoothness constraint that I mentioned earlier, that is new to Euclidean signature, one finds that the area plus beta omega j becomes completely independent of C and beta, and precisely gives the extremal entropy that people saw in the past for the attractor black holes. So this explains why the index of these black holes actually was correctly computed by their area at extremality. And more generally, one can, this is just a trick to, the thing that I showed previously is just a trick to computing the free energy of the black hole. The actual path integral computation that we did was to compute the en-shell action for these solutions. And the en-shell action is quite complicated because it involves both contributions from scalar fields, from the gauge fields, and from the metric. But overall, the conclusion is the same. The en-shell action is given by beta times the BPS energy of these black holes. That's given by this function known as the central charge, times the intersection product between the charge at the north pole and the charge at the south pole. And this from the smoothness condition, this intersection product precisely reproduces the entropy function evaluated at the asymptotic charges of the black hole. And this is what captures the log and the difference of dB and dF, and the extremal black hole entropy. And one can generalize this procedure, just like we did before, to compute the index of any multi-center solution. So these are analogs of the Denef Bates solution. To summarize, we have found a series of gravitational solutions that contribute to an index. Their general feature was that asymptotically, they look like R3 times S1 with radius, with S1 having a circumference beta, and they have fixed angular velocity with beta omega equal to pi. They interpolate between these asymptotic geometries and some geometry in which the emblackening factors has poles. The poles can be viewed as the north and south pole of some rotating black holes, and I can put as many black holes as I want in this space. And by looking at these solutions, we found subtle analogs of the attractor mechanism for both the temperature and the scalar moduli. The moduli are independent at the north and the south pole, and as a consequence, the free energy is also independent of the asymptotic moduli and has trivial beta dependence. And as an outlook, in the past couple of years, a lot of progress has been made on trying to localize the path integral in supergravity with index boundary conditions. But this was only achieved in the limit when beta went to infinity, because the localization computations that were done so far in supergravity have asymptotically ADS2 times S2 boundary conditions. However, these solutions, we see that we can work at any beta. Namely, we can try to find not solutions of supergravity that have asymptotically these boundary conditions, but rather just find geometries that have killing spinners, but don't necessarily satisfy all the equations of motion in supergravity. And that should give us what the localization locus is when trying to do localization with asymptotically flat space boundary conditions. I don't know whether or not the metric can still be written in terms of a simple harmonic function, just like we did before, but this is something that's worth exploring. And let me mention a few problems, open problems. The first question is about localization. What is the analog of the localization locus with these new boundary conditions? The second problem, it occurs for multi-center black holes. People have studied the moduli space of these Denef Bates solutions in order to compare with the index in string theory. And naively, it seems that the moduli space that we get for the solutions in Euclidean signature at non-zero beta seems to be different than the moduli space of solutions in Lorentzian signatures that people find in the past. And the question is, even though the moduli spaces might be different, do the volumes of these two moduli spaces still agree? And that requires a pretty subtle computation. And finally, the solutions that I described in the first part of the talk that compute trace -1 to the F e to the minus beta h didn't actually require us to work in a theory of supergravity. If I just take Einstein-Maxwell theory in our own universe and compute this trace through a Euclidean computation, I will still find that the leading saddle contribution to the gravitational path integral takes the form of an index. Which means that this quantity trace of -1 to the FE to the minus beta h is still approximately, behaves as if the theory is approximately supersymmetric, even if I just work in a regular gravitational theory, like the theory that we have in our own universe. So this brings up the question if SUSY is an approximate symmetry all the time in quantum gravity at high energies that probe the spectrum of black hole microstates. Thank you very much. Any questions?
Questions?
Yeah, so for this second point, could you elaborate a bit on how the moduli space is different?
Yeah, so for instance, the simplest case is the case of a two-center black hole. So for two-center black holes, the solution that Denef found has the distance between the black holes completely fixed. So there's actually no moduli space. What happens is that as you tune the asymptotic values of the scalars, the distance between the two black holes can run off to infinity and the solution disappears. And on the boundary side, they associate this phenomena, or he associated this phenomena to wall crossing. Here, if I consider the analog of the two-center solution, that's specified in terms of two north poles and two south poles. And the smoothness conditions that you impose, there are only, I think, 4 smoothness conditions. And if you fix the center of mass of the black holes and fix an axis of rotation, you're still left with free unknown parameters. So like there's still a 3-dimensional moduli space that's described by how the relative position between these two north poles and these two south poles. Now, the expectation that we don't know, because that depends on the measure that you choose on the moduli space. So there was a proposed symplectic measure that people used for this moduli space that we're trying to understand whether it's applicable or not to these solutions. And we believe it is, but we haven't gotten around to computing the volume of this symplectic manifold. But presumably what it should give is something that's, again, temperature independent and independent of the values of the moduli at infinity. But that's something that's very non-trivial to see.
Any other questions? If not, thanks, Luca, again.